Suppose that a1 is equal to 2 and the sequence an satisfies the recurrence relation a subscript n minus 1 divided by n minus 1 is equal to a subscript n minus 1 plus 1 divided by n minus 1 plus 1, and that is valid for all n greater than or equal to 2. Then what is the greatest integer less than or equal to summation of a subscript n squared, and the summation is from n is equal to 1 to 100. To solve this problem, the following two formulae will be needed. Formula 1, summation of n squared when n varies from 1 to n is given as n multiplied by n plus 1 multiplied by 2n plus 1 whole divided by 6. And the second formula is summation of 1 by n squared when n varies from 1 to infinity is pi squared by 6. It is given in the question that a subscript n minus 1 divided by n minus 1 is equal to a subscript n minus 1 plus 1 divided by n minus 1 plus 1 for all n greater than equal to 2, and also a1 is equal to 2. From the given equation, a subscript n minus 1 divided by n minus 1 is equal to a subscript n minus 1 plus 1 divided by n minus 1 plus 1, which can be further simplified to a subscript n minus 1 plus 1, and in the denominator it will become n. Now let us examine this equation giving different values of n starting from 2, because this formula is valid for n greater than equal to 2. So when n is equal to 2, we get a subscript 2 minus 1 divided by 2 minus 1 is equal to a subscript 2 minus 1 plus 1 divided by 2 minus 1 plus 1, and that is a1 plus 1 divided by 2, and that is equal to 3 by 2, because a1 is given to be 2, or a2 minus 1 is equal to 3 by 2, or a subscript 2 is equal to 5 by 2. This can be written as a2 is equal to 2 squared plus 1 divided by 2, or n squared plus 1 divided by n when n is equal to 2. Similarly, when n is equal to 3, we get a subscript 3 minus 1 divided by 3 minus 1 is equal to a subscript 3 minus 1 plus 1 divided by 3 minus 1 plus 1, and that becomes a subscript 2 plus 1 divided by 3 is equal to, we have just now found out a2 is equal to 5 by 2. Putting that value, we get a subscript 2 plus 1 divided by 3 is equal to 5 by 2 plus 1 divided by 3, and that is equal to, after a little bit of simplification, 7 by 6. Or a3 minus 1 divided by 2 is equal to 7 by 6. Therefore, a subscript 3 minus 1 is equal to 7 by 3. Hence, a3 becomes 10 by 3, which can be written as n square plus 1 divided by n when n is equal to 3. Similarly, we can proceed to find the value of the given equation when n is equal to 4. And again we find n is equal to 4 after following the same steps as before is equal to 17 by 4, or again n square plus 1 by 4, where n is equal to 4. Proceeding like before, we verify the equation for n is equal to 5, and we get a subscript 5 minus 1 divided by 5 minus 1 is equal to a4 plus 1 divided by 5 minus 1 plus 1, and after simplification that becomes 21 divided by 20. And therefore, a subscript 5 minus 1 divided by 4 is 21 divided by 20. That yields the value of a5 as 26 by 5, which is again n square plus 1 divided by n when n is equal to 5. So we can guess that an is equal to n square plus 1 divided by n for all values of n. However, this is only a guess, not a rigorous proof. We can prove this by the method of induction. Till now it is a conjecture. It will become a proof only when we have proved it rigorously. Let us assume that an, that is a subscript n, is equal to n square plus 1 divided by n. Let us call it equation 1. The formula given in the question is a subscript n minus 1 divided by n minus 1 is equal to a n minus 1 plus 1 divided by n. Let us call it equation 2. If equation 1 is true, then equation 2 can be rewritten as a n plus 1 minus 1 divided by n plus 1 minus 1 is equal to a subscript n plus 1 divided by n plus 1, where we have replaced n as n plus 1 and n minus 1 as n to go to the next term. So we get a subscript n plus 1 minus 1 divided by n is equal to, because an is known to be n square plus 1 divided by n, or we are assuming that, then a subscript n plus 1 minus 1 divided by n is equal to n square plus 1 divided by n plus 1 divided by n plus 1. And after little simplification, the numerator becomes n square plus n plus 1, and the denominator becomes n multiplied by n plus 1. Or by cross multiplying both sides by n, we get a subscript n plus 1 minus 1 is equal to n square plus n plus 1 divided by n plus 1. Therefore, a n plus 1 is equal to n square plus n plus 1 divided by n plus 1 plus 1, and that is equal to n square plus 2n plus 2 divided by n plus 1. We can rewrite this as n square plus 2n plus 1 plus 1 divided by n plus 1, and that is equal to n plus 1 whole square plus 1 divided by n plus 1. Hence, it is now proved that if an is equal to n square plus 1 divided by n, then an plus 1 is equal to n plus 1 whole square plus 1 divided by n plus 1. That is, if we assume that the nth term is as per this formula, the n plus 1th term will be as per the same formula with n plus 1 replacing n. That is, if A2 satisfies the formula, then A3 also satisfies the formula, and if A3 satisfies the formula, A4 will satisfy it, so on and so forth. So this formula should hold good for every value of n greater than or equal to 2. We have already checked that A2 indeed satisfies the formula. Hence, the formula holds good for all values of n greater than or equal to 2. Therefore, now it is proved by method of induction that an is equal to n square plus 1 divided by n. Since an is equal to n square plus 1 divided by n, we get an square is n to the power of 4 plus 2n square plus 1 divided by n square, and that is equal to, if you divide all the terms of the numerator by n square, we get n square plus 2 divided by 1 divided by n squared. If you take summation of an square while a is varying from 1 to 100, then on the right hand side also we'll have to take the summation of n square plus 2 plus 1 by n squared, while the summation goes from 1 to 100. And the summation of the three terms can be segregated into three separate summations like this. The first summation is for n squared, the second summation is for the quantity 2, and the third summation is for 1 by n squared. As discussed at the beginning, summation of n squared is equal to n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6, and in this case the summation is from 1 to n, which is 100, so this becomes 100 multiplied by 101 multiplied by 201 divided by 6, and if you do the multiplication, the value comes out to be 338,350. And summation of this term n is equal to 1 to 100 of just 2 will be 2 plus 2 plus 2 plus 2 100 times, and that will be 200. But what is summation of n is equal to 1 to n is equal to 100 of the term 1 divided by n squared? We do not know this. However, we know from formula 2, which we had written down at the start of the video, that summation n is equal to 1 to infinity of 1 by n squared is pi square by 6. Here, the summation is from 1 to infinity, not 1 to 100, that is required by us. But since summation of 1 to infinity of the term 1 by n squared can be written down as sum of two summations, the first one being n is equal to 1 to infinity 1 by n squared, and the second term is n is equal to 101 to infinity 1 by n squared. We come to conclusion that summation of n is equal to 1 to infinity of 1 by n squared is greater than n is equal to 1 to 100 1 by n squared, because 1 by n squared summation from 101 to infinity is positive, since it is a sum of positive terms. So we get pi squared by 6 is greater than n is equal to 1 to infinity summation of the term 1 to n squared, or summation of n is equal to 1 to 100 of the term 1 by n squared is less than pi squared by 6. We also note that summation of n is equal to 1 to infinity 1 by n square. If we write down the terms, it is 1 plus 1 by 4 plus 1 by 9. Like this, it will go on up to 1 by 100 squared. Obviously, since the first term is 1 and other terms are all positive, and adding to it, this value is greater than 1. Hence, this term has to be greater than 1 and less than pi square by 6, or 1 is less than summation n is equal to 1 to infinity 1 by n square, which is less than pi square by 6. Now, we know pi is approximately equal to 3.14159. Therefore, pi square is less than 10, or pi square by 6 will be less than 2. So, pi square by 6 is between 1 and 2. That is 1 less than pi square by 2, and pi square by 2 is also less than 2. Therefore, this term summation of n is equal to 1 to 100 of the term 1 by n squared will also be between the integers 1 and 2. That means it will be greater than 1 but less than 2. Finally, since we have found out the value of the summation of an squared over the range of n varying from 1 to infinity is equal to the summation of three separate terms, that is summation of n square, summation of 2, and summation of 1 by n square over the same ranges of the value of n, that is from 1 to 100, and we have already found out the values of these three terms separately. We can add them together to find the value of the sum of an squared over the range of n from 1 to 100 as this term being 338,350, the second term being 200, and the third term is a quantity that is more than 1 but less than 2. If you add these two terms, it becomes 338,550, and the last term, that is this term, becomes a fraction or a decimal which is 1.xyz dot 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 dot. So this, that is summation of an squared from 1 to 100, will be more than 338,550 plus 1, but less than 338,550 plus 2. So the greatest integer, which is less than or equal to summation of n is equal to 1 to 100, an squared is equal to 338,550 plus 1, that is 338,551. That is the answer.